So today we're very pleased to have Mark Bell from Warwick. Mark will be joining us next year as a due postdoc, and today he'll tell us about something like planes, trains, and automorphisms.
Very good. Excellent. Thank you very much. It's a pleasure to be here. Yeah, unfortunately, in coming here, I didn't actually get to do the infamous JFK to O'Hare flight from the movie. So I think I'm going to use this as sort of an excuse to tweak what I'm going to do ever so slightly. So in the original plan, we were going to sort of talk about the automorphism group of a punctured plane. And this was sort of going to be closely related to the braid group in some sort of nice way. And what we were going to do was going to be sort of very carefully constructed. So in fact, it would actually generalize to all higher genus surfaces and so on. But having sort of thought about it a little bit more, I think actually it's slightly easier to explain if I use just a little bit of genus. So maybe the moral for today is I'm going to do things in sort of genus 1, genus 2, something like this. And it's going to generalize to higher genus, but also down to lower genus as well. So if you want to do the spherical braid group or just the braid group itself, you can do that as well. Right, okay, so I guess the aim for today is to do something involving the conjugacy problem. Which is actually a very sort of general problem that was first really sort of studied by Dane back in the early 1900s. And part of the reason why it's so general is that actually it requires very little. So all you need is a group, G, and maybe to make it sort of a little bit more consistent or a little bit more rigorous, I'll have some nice finite generating set for this group. And the question really is just, well, actually, if I give you, say, two elements of this group, maybe I'll give them to you as, say, words in this generating set or something like this, I'd like you to decide if G is conjugate to H. So does there exist a W such that G is WH, W inverse? And sort of rather famously, this problem is actually totally undecidable. So we don't really have a chance of saying anything about this in sort of full generality, but maybe for today what we'll do is we'll focus on something where there's some topology to guide us, and as a result we can actually make some progress. So I want to say that we're only going to think about one particular family of groups, so this is going to be when G is the automorphism group of some surface S. And so for me, automorphism here really means mapping class. So this is actually, we'll look at the homeomorphisms of S. And maybe to make my life easier and drawing pictures easier, we'll just do the orientation preserving ones today. And we'll think about these things up to isotopy. So this is also the mapping class group of S. And so there's supposed to be sort of some very nice sort of topological interpretations for the conjugacy problem. Perhaps the nicest one that I can share with you, if I jump over to this side, is, well, if you want, one of the things you might try and do is sort of get some sort of baby steps into the world of three manifolds from these things by looking at their mapping tori. So we have some nice surface like this, and we have one of these mapping classes, one of these homeomorphisms up to isotopy, and we can use this to build a three manifold by taking a product with our surface and an interval, and gluing the bottom copy of our surface to a top copy using the mapping class that we have available to us. And this is sort of a really nice sort of three manifold because of the fact you can study a lot of its properties simply by studying the actual mapping class itself, H. So this will be the mapping torus, say, MH. And the nice result here that actually is not too hard to show is that if you want to, say, classify these things So this is, I guess I'm really classifying this up to fiber-wise isotopy, fiber-wise homeomorphism, sorry. These two things are homeomorphic, actually, if and only if H is conjugate to G, or G inverse. So if you want to say anything sort of reasonable about classifying fibred manifolds, you have to do something involving the conjugacy problem sooner or later. So I think actually the algorithm that I want to sort of talk about today, or the procedure that I want to talk about today, I'm going to try and put like all of the complexity, the computational complexity theory stuff as late as possible. So hopefully we might even run out of time and I won't have to say anything about it. And I'll get away, hopefully for the minute, by actually just saying that this technique that we're going to use is effective. And what I mean by that, I mean as in you can actually use it to solve examples of the conjugacy problem. So let me switch the computer for a minute. So hopefully this will actually work. Maybe not. And why does this not match that? Let me try unplugging this and plugging it back in. I'll tell you what, let me kill this and start it up again. For some reason this display doesn't seem to be matching my display. Maybe I can change some settings in here. Screen display. There we go. Mirror displays. That should help. Fantastic. Okay. Let's reopen this. Okay. So this is some software I wrote a little while ago. It's called Flipper. If you want to sort of like follow along or anything, you can get a copy of it off of my webpage or something. And Flipper likes surfaces and it likes mapping classes as well. And so in particular in this sort of main window here, Flipper's got a surface already loaded into it. It's sort of opened the surface out into some nice polygon, and it's been sort of very careful to sort of color code things so you can see what the original surface was. So in this particular case, this is an example of a torus. You glue the left side round to the right side and the top side down to the bottom side. But actually there's a sort of subtlety here, which is that the gluing that I've got on each of these sides doesn't extend to the vertex. So for sort of technical reasons, actually this isn't the surface of genus 1. This is actually a once punctured torus. And on this particular example, Flipper knows about a couple of curves. So there's this horizontal curve that runs from the left side to the right side, and this vertical curve which runs from the top to the bottom. And whenever you have a curve on your surface, there's sort of a nice construction that lets you get a mapping class straight away. And so this is to do a Dane twist along this curve. So I think this is a picture worth drawing. So when you have your curve, let's make a color. So you have some curve gamma which runs around some nice little annular neighborhood. Well, what you could do is you could take your surface, you can cut it open along gamma, rotate one of the boundary components 360 degrees and glue things back together. So actually if I just draw this picture after doing the twist, so this is the twist about gamma, everything looks pretty much the same. In fact, you can't see any real difference until I draw some extra markings on to sort of help show what's going on. So maybe there's another curve that runs through here like this. Well, now afterwards, as it approaches gamma, it has to turn and spiral all the way around before coming out the other side. So Flipper not only knows about these curves, it also knows about the Dane twists along them. So these are listed just a little bit lower. And Flipper's very happy to sort of apply these twists to curves and things that are drawn on the surface. So for example, here's this nice vertical curve that's been drawn on the surface, and A was the horizontal one as well. So if we do a twist about A, this vertical one now comes up, diverts round to the right, goes all the way around once, before continuing on to the end. And it's always worth doing some kind of like sanity checking or something. So if we apply the inverse map, yeah, we do actually go back to the vertical curve. And Flipper's very happy to sort of play around and mix and match these things as much as you want. So we can do a few twists about A, and then maybe a few twists about B, and then a few inverse twists about A, something like this. These are very, very straightforward from its point of view. So I'm supposed to sort of consider these two guys as my generating set for the mapping class group, and try and actually solve some conjugacy problems. So I picked a few sort of elements from here sort of earlier on today. So let me actually put these guys in. So we want A, B inverse, and I think the other one was A, B, A, B, B, B maybe. And what we can do, if I open these guys up, is actually ask, which of these mapping classes are conjugate to another. So Flipper will think for a few seconds maybe, and tell us that in this particular case, these two guys aren't conjugate. Or maybe there's this one down here, and this one, for example, and yeah, these two guys are conjugate. I should say maybe the once punctured torus is kind of a very special surface. It's got sort of some really nice covers or something that you can take advantage to. So perhaps to sort of do something that maybe doesn't appear in the literature or something, we could try and do a little bit more complicated example. So if I draw a new surface in this thing, so let's pull this up like this. So just as before, I'm going to glue opposite sides together, and I'll make it a little bit bigger. So now instead of being genus 1 with one puncture, we're still on genus 1, but now these two punctures in the center are identified and the 4 punctures in the corner are identified. So actually we're on a twice punctured torus instead. And again, I can sort of recreate these twists about these curves that we had before. So I think there's this nice chain of curves that go through the surface like so, something like this, and then I think I have this third one down here. And these 3 guys, again, generate the mapping class group for the twice punctured torus. And Flipper's very happy to do these kinds of twists and these kinds of moves. So again, just to sort of pull up some random words almost, so A, B, B, C inverse, and let's go for something long, A, B, B, C, C, B, C, B, A, B maybe. So I think these guys have been cooked up so they are conjugate. Okay, and this is where it sort of gets slightly nerve-wracking. Oh, okay, but these two things do match up, so this is okay. This is what I was expecting it to be. So this is sort of something that you can actually practically do. We can do higher genus surfaces. We can do sort of these penna-like examples as well. These are all good fun and something that Flipper's very, very comfortable with. And it produces nice pictures as well, which is always nice. Okay, so let me get rid of this. Right, okay, so maybe having actually shown this is somewhat viable to do, I should say something about just how much effort actually Flipper was really going through in the background. So if you like, what you can do is you can think of Flipper as this sort of black box or something where you put in 2 of these elements, G and H, and after a little while out pops either yes, these guys are conjugate, or no, these guys aren't conjugate. And unfortunately, actually, in the worst case scenario, the amount of time you have to actually wait for this process to complete is unfortunately an exponential function of the length of G and the length of H. But one of the nice things that Flipper does is it doesn't only give you the yes-no answer. You also get a little bit extra out when you do this kind of calculation. So not only do you get whether or not these things are conjugate or aren't conjugate, you actually get a proof. You get an entire, complete, written-out proof that these two things are conjugate or that these two things are not conjugate. And in fact, this proof is so nice and so lovely that you can use it in Flipper itself. So if for some reason you just forgot whether or not these two maps are conjugate or not, or you had a friend who you wanted to convince that these two mapping classes were conjugate or not, well, what you could do is you could give them these words along with the proof, and they can plug all three into Flipper. And now, again, of course, Flipper will tell you the right answer, so it'll either tell you yes or no, these things match up, or they don't. But now, instead of taking an exponential amount of time, it will only take a polynomial amount of time in the word lengths. So this is sort of really, really, really nice from a computational point of view. And in many ways, it's sort of actually reminiscent of sort of how people do maths. You have some very hard problem, and you go to some very eminent professor in your field, and you ask them to think about this, and they go away and they think for a very, very long time. And at the end, they come back to you and they say, yes, your conjecture is correct. It's an actual theorem. Or alternatively, they say, no, there's a counterexample to what you were hoping. But they're even better than that, because not only do they tell you whether or not the theorem is correct, or there's a flaw in it, they either give you a proof or they give you a counterexample. And because of the fact they were so brilliant and so eminent, their proof is very understandable. And so rather than sort of doing this naive sort of process where you have to go through all of the trains of thought that they had, you can be sort of directed. You don't have to go through and examine all these dead ends. You just get to follow their ideas. And so this is sort of a very nice and very natural thing that comes up in computational complexity theory. So I should say, actually, the computer scientists or something would want me to say, so this is actually the definition of the complexity class NP intersect code, NP. And this is the NP as in P versus NP and so on. So this side is to do with getting a proof when the answer is yes, and this side is to do with getting a proof when the answer is no. And because of the fact we're in the case, well, it doesn't matter what the answer is, you always get the proof as well. It's in the intersection of both of these things. So let me try and say a little bit about what goes on here. I should say, perhaps, first of all, there's sort of a very, very natural proof that two things are conjugate. If we have these two mapping classes, and it turns out that after Flipper's thought for a very long time that the answer is yes, then perhaps the most natural thing for me to provide to you in order to convince you that these two things are conjugate is just to give you the conjugating element. And this is a great idea, and is actually what Flipper does in the yes case. But unfortunately, you have to worry about these things, because at the end of the day, you've got to sit down and you've got to be able to reproduce the result from the proof in only a polynomial amount of time. And so for this to happen, you need so you actually need two theorems. So the first is a theorem of Jing-Tao, which says that actually, if G is conjugate to H, then there is a conjugator whose length is bounded by some linear function of the length of G plus the length of H. Because unfortunately, you might be in the scenario, and more generally, there are groups where this is the case, where even when you have two elements that are quite small and that are conjugate to one another, the smallest conjugating element that takes one to the other is absolutely enormous. And there's no way around this. But fortunately, in the case of the mapping class group, Tao actually showed that this is the case, and you don't have to worry too much about this. Of course, there's actually a second subtlety here, which is that even if I give you the conjugating element, you've still got to do some work. You've got to actually check that G is the same element as WH, W inverse. And so there's a second thing that you actually need. So you need a theorem. I guess this is due to Moshe, which is that the mapping class group has a polynomial time solution to the word problem. So this idea of actually just providing you with a conjugating element does work, but only thanks to these two theorems. So it's actually the no case that's sort of a little bit more subtle and involves more details. So to actually do this, I think probably the easiest thing for me to do is to discuss how you would actually build some kind of conjugacy invariant that hopes to tell these two things apart. And so maybe the best place to sort of give you an idea of the proof is actually in this once punctured torus example. So let's see what we can do here. So I should recreate this picture that Flipper was drawing. So we have this square with opposite sides identified, and our puncture is right here in the corner. And what I can do is I can actually sort of leverage sort of some of the linear algebra techniques actually, because of course this guy is covered by r squared minus z squared. So there's a cover up here which is r squared minus z squared. And I'm quite happy to sort of manipulate matrices and things like this. And this is a very sort of natural way of describing elements of the mapping class group, for example. So if I take my favorite mapping class, say H on here, this is actually a very nice matrix. So the matrix, say 2, 1, 1, 1. Then this matrix up here, well, I guess it has determinant 1 or something, so preserves the lattice and so descends down to a nice transformation on the torus here. So perhaps the nicest thing that I can say about this matrix is that actually it has some invariant structure that I want to take advantage of, and in this case, the sort of the more natural language that you would use to describe this is it has an eigenvector. And so the eigenvector in this case is the vector phi 1. So here phi is this golden ratio, 1 plus root 5 over 2. And I could maybe sort of work out some nice numerical properties of these numbers. In particular, actually, the thing that turns out to be the most natural thing to use is the continued fraction expansion. So if I have phi, I can write this as 1 plus 1 over 1 plus 1 over 1 plus, and so on, going all the way down. This notation is a little bit space consuming, so the more compact way of writing this is 1, 1, 1, 1, 1, something like this. So what happens under conjugation? Well, if I take a second matrix, I guess this is my second favorite matrix in SL2Z, and I conjugate it by this thing, well, hopefully all of these things should change in a nice predictable way. So here's a second example. So I think I want 7, 3, 2, 1. And when I conjugate, so I have to write my matrix again, and then 7, 3, 2, 1 inverse. Well, conjugation changes the eigenvectors in a very predictable way. So the eigenvector down here is now, of course, just going to be 7, 3, 2, 1 applied to phi 1. And if I expand this out, okay, so I'll renormalize and rescale so that the second entry is still 1 again. But this is, and let me make sure I get my numbers correct, otherwise this won't work out. This is, yeah, this is actually now 9 minus root 5 over 2 and 1. And we could repeat the exact same process for this entry up here. And so this is something I did before. And allegedly, the continued fraction expansion for this thing is now 3, 2, 1, 1, 1, 1, and so on. And so in both of these cases, these numbers here are quadratic irrational, so I expect the continued fraction expansion to eventually become periodic. But the reality is actually that that you can expect a lot more of this. This infinite repeating sequence, which crops up in both cases, is actually a total conjugacy invariant. So given these pieces, this infinite repeating periodic pattern, you can actually reconstruct one particular conjugacy class of mapping class back again. So this stuff here is a total conjugacy invariant. So the reality of what's going on really is that we have this sort of nice periodic pattern, and conjugation is sort of letting us hide it under a small amount of junk. So if I take any old matrix that you might be interested in, and I work out what its eigenvector is, and then I work out the continued fraction expansion, well, I know that eventually what's going to happen is after I've removed this little bit of noise that you hit at the beginning by conjugating, I'll hit this periodic part, and this periodic part will let me decide whether or not these two matrices are conjugate to one another. So the idea really, in the more general setting of the mapping class group of a surface with more genus or with more punctures, is just to replicate this exact argument. We need some kind of generalization of eigenvectors, and we need some kind of generalization of continued fraction expansion, but at its heart, this is what it boils down to. So I guess, yeah, I should leave that one up. So I guess we should start with trying to generalize this idea of an eigenvector. And I guess, again, just to make my life slightly easier, I want to put like a little technical caveat into this thing. So the technical note here is that we're only actually going to do this, at least today, in the case where H is pseudo-Nosov. So this is infinite order and irreducible. It kind of turns out that this is the most interesting case to do, and if you can do it in the pseudo-Nosov case, well, in the reducible case, you just sort of break it down into pieces and work on each piece individually and combine your solutions back together in the end. So the first order of business is to try and generalize an eigenvector. But fortunately, in the pseudo-Nosov case, most of this was already done by Thurston. So even though we don't have maybe this nice structure of a linear group like SL2Z or something, we still have a projectively invariant lamination. And in this example over here, this eigenvector, this line of irrational slope that filled up the torus, it was very there was a very sort of nice and natural way to describe this thing. We have this vector of two numbers, and we will need to sort of replicate that over here in the more general side. So actually, I guess this picture as I've drawn it is slightly misleading. I mean, this surface here, it's supposed to be some kind of hyperbolic surface. So it should actually have some kind of hyperbolic geometry associated to it. So perhaps the more realistic picture is if I draw my square as some kind of hyperbolic square, and this invariant lamination as some kind of geodesic lamination on the surface. So something like so. And now the trick, if you want to try and sort of represent these things from a combinatorial point of view or from a computational point of view, really is to do the following. Well, what you do is you sit right at the very back of the lecture theatre and you squint. So when you do this, you sort of lose all of the fine-grained detail, and all you can see is the more general, broad geometric structure. So something like the following drops out. So you see these big pieces which connect together like so. And I guess the widths of these pieces should be some nice geometric properties. So in this particular example here, the width of this piece should be phi, and the width of this bit of ribbon here should be 1. It gets a little tedious drawing these pictures like this, so most of the time we sort of collapse them down to a nice simple graph. So I'll start doing that. So something like the following. So I have phi, I have 1. I guess there's a piece in the middle here actually, and its width should be phi minus 1. That's 1. That's fine. And so by sort of doing this kind of construction, what we can do is we can take our lamination that we have on our surface and actually just describe it purely via some kind of graph with weights on the different edges. So this graph is actually a train track. And by using sort of different train tracks in different combinations, you can actually end up describing you can end up with the ability to describe all the different laminations you could ever possibly draw on the surface. So this provides sort of a nice combinatorial and computational way of talking about these things. So I guess for something like this, we have this train track with these 3 edges on here. So maybe we should have some kind of vector associated, which should be something like 1 phi and phi minus 1. So if this is going to be our sort of generalization of an eigenvector, well, we need some kind of generalization of the continued fraction expansion as well. And this is sort of, again, a very analogous construction. Unfortunately, it's not totally analogous to the way that I wrote down the continued fraction expansion here. Rather than doing this business of sort of subtracting off 1 and then taking a reciprocal and subtracting off 1 and taking a reciprocal and so on to actually pull out all of these coefficients one at a time, really because of the fact I don't quite understand what division is, particularly over in this more general setting. But what I can do instead is actually get this continued fraction expansion of phi in a different way. Because what I'd really like here is, I mean, I had to make some kind of choice. I had to rig things over here. And the way that I rigged it was by putting a 1 down here. Because the reality of it is that the eigenvector doesn't care about what the entry is down here. You could multiply all these numbers by pi or by 7 or something, and it shouldn't affect the result. So perhaps the sort of the nice way of getting this continued fraction expansion of phi relative to 1, or more generally like root 2 phi relative to root 2, is to actually replace this process purely by subtraction. So to actually extract all of these components, what I can do is I can take my vector, and I guess now I'm going to do lots of subtractions, so maybe I kind of want to do this with like decimals or something. So phi is about 1.6 something, and I have 1 on the bottom. And what I do is I replace the largest number with the largest number minus the smaller number. So so 1.6 is bigger than 1, so I'll do the subtraction top to bottom. So now I've got 0.6 and 1. And now I'll repeat this process, but things have swapped over now. The highest term is now on the bottom. And so now I'll have 0.6 and 0. Okay, I guess this is a bit more than 0.6, so it should be 0.3 something, and so on and so on and so on. And when I do this process, what will happen is I'll have to alternate as I go along. I'll start off here, subtracting away from the top entry, and after some number of subtractions, I'll have to swap, and I'll have to start taking away from the bottom entry, because the bottom entry has now become larger than what the top entry is. So in this particular case, I do 1 subtraction before I have to switch, and then I start taking away the top number from the bottom number, and again, I only get to do 1 step before I have to switch back again, and I do this process again and again and again, and each time I keep track of how many times I do the subtraction on top or how many times I do the subtraction from the bottom, and record down these digits. And these digits exactly record the continued fraction expansion. So if I take one of these eigenvectors and I rescale by any positive real number, these entries will change by some positive real number, but so will all of these ones in this chain. And in particular, all of these how many times I did each subtraction won't change. So it's a sort of a nice, very natural, very independent of this replicate choice I made by enforcing a 1 down here. So on the sort of the train track side of things, to replicate this, you have there's this notion of splitting, which actually, I mean, if you want to sort of think about it purely as like a combinatorial move on train tracks, is a perfectly valid thing to do. So we have some train track and some bit of it that looks like this, and the different edges that you see here have different weights associated to them, different widths to the original ribbon. So maybe there's A, B, C, D. I guess there's E in the middle, but this has to be the same thing as like A plus B. There's some criteria that you have to satisfy in these in terms of these numbers. And what we want to do is we want to sort of like pull this guy apart and see some of the finer detail, because after all, what's happening is we have some of our lamination is flowing in here, and then it flows across E and either exits through C or exits through the branch with a D written on it. So the idea is to pull this apart and to do a split. And when this happens, so you either end up with a picture which looks like this, or there's a second possibility for what can happen. Which is that, okay, I guess I can put it to the side. Or this diagonal could go in the other direction. But there isn't actually a choice to be made here. I mean, the numbers that you have on each one of these 4 edges determines which one of these 2 cases you drop into. It'll be something like, well, okay, so I guess I can put the weights on these things as well, because you'll know these after you do the calculation. So these still have to be A, B, C, D, A, B, C, D, and now there's some new edge like E prime, maybe. And in this case, so E prime, you have a lot that comes in on A, and some of it diverts out through C, so the rest has to go through E prime, so this is A minus C. And here it goes in the other direction, so E prime is C minus A. And which one of these two cases you'll end up in will be determined by which one of these two quantities is positive or something like this. So actually the or there is sort of a bit misleading. Perhaps you don't get a choice in the matter. You just have to go to whatever the numerics tell you. So to replicate this business of computing the continued fraction expansion, the idea is just to actually do exactly this splitting process because of the fact that it has such a natural analog to this subtraction up here. So just repeatedly split the branch with maximal weight. So I guess in this example back here, for example, this branch that I want to do the splitting along is actually hidden a little bit. It goes off of this edge and comes back on here, and it's the only place where I could apply this splitting, so I don't have to worry too much about finding the one with the maximal weight. And after I do the splitting, I'll pull this apart, and I'll be able to see the lamination in just a little bit more detail. So the fun result. So this is a theorem of Ian Agel, is that actually when you do this, you sort of produce this sequence of train tracks, the sequence of weighted train tracks, and this sequence of weighted train tracks is eventually periodic. So there's some minor details about what I actually mean when I say eventually periodic. So I have to actually put in some things here. So up to rescaling and re-embedding. So what I mean by this is that you might hit the exact same train track, but you might see all of the numbers have been rescaled by √2 or something like this. Or you might come back to the exact same train track, but it's just embedded in the surface in a different way. So when it comes to deciding whether or not two train tracks are equal in this particular case, you should allow yourself to rescale the weights by whatever real number you need. And you should also only actually care about the combinatorics of the underlying train track. You should only care about how these things are glued relative to one another, not necessarily with respect to the embedding. Yeah?
Is there always the unique maximal weight?
No, there isn't a unique maximal weight, which unfortunately means that so if you want to do what Agel says explicitly, he says do all of them simultaneously, because fortunately this picture is these pictures, if there's more than one that occur in the diagram, then they're disjoint from one another. You can't this branch here, this branch that runs across the middle here, can't possibly also be in the same configuration here, because it has this. Sorry, maybe I should emphasize it a little bit more. There's something wrong with the tangencies at the end of this branch here. If you want to do the splitting on this branch, you have to have these nice smooth cusps coming in and going out of each side. And unfortunately, if you look at, say, this branch here, it doesn't have the nice smooth cusps at this end. So that you can't ever do a splitting of this branch. And similarly for all the others. So if you do end up with a tie for maximal weight, you should do both simultaneously. That's the technical way to get around this. Okay, so what happens is that we end up producing this sort of nice sequence of train tracks, and eventually this sequence form some kind of periodic cycle up to rescaling and re-embedding. And this periodic bit at the end is really, really nice, and in particular actually acts as a total conjugacy invariant in just the same way as the periodic part of the continued fraction expansion did in the case of quadratic irrationals. So the entire aim of Flipper really is just to take some kind of nice train track containing some projectively invariant lamination and just to repeatedly do this splitting process. And eventually it runs into one of these cycles which it can detect in some nice way, and then it gets to stop and just and uses this as a total conjugacy invariant. So the only bit that I should really add, which is perhaps the bit that I actually did, so this this business of doing this repeated splitting and getting to some periodic cycle is that actually in this theorem what you can do is you can replace the word eventually with some quadratic function of the length of h. So if you take some projectively invariant lamination and you manage to get your hands on that, then from that point on you know you've only got a polynomial amount of work left to do. So in particular, if you want to try and convince your friends of the fact that these two mapping classes aren't equivalent to one another, well, what do? Well, you hand them the projectively invariant lamination, and then they can go away on their own and actually construct this total conjugacy invariant purely from that. Because after you give them this invariant lamination, that's it. They're on their own and they can solve it. They can solve this entire thing in polynomial time. So getting the projectively invariant lamination, that's the hard bit. That's the bit that unfortunately takes potentially exponential time for Flipper to do. But once it's done that, everything that follows just happens in a polynomial amount of time.
So when you say eventually, so in that time you encounter the start of the conjugacy variant, or you find the conjugacy? And there's like there's the length of the tail, and then there's the length of the conjugacy cycle itself.
Right.
Are those both bounded quadratically, or?
So if you want to be a little bit more subtle, so you're right. There's two quantities here. So there's the length of this bit, and there's the length of the entirety of the cycle that sits here. And so what you can do is the actual proof is that the length of this cycle is at most a linear function of h, and the length of the pre-periodic part here, unfortunately, has a quadratic bound on it. I should say, this quadratic bound is almost certainly not optimal. There's going to be hopefully some kind of nice cube complex type structure that should let you get this quadratic down to a linear, just like this one is. But from a computational point of view, perhaps you don't care quite so much because polynomial is polynomial, and the complexity classes don't distinguish really between linear and quadratic or anything like this. So if you want to sort of like care about the subtleties, there's a slightly better bound on this chunk, but the remaining bit, or the bit that you actually have to really worry about, only has a quadratic bound on it, unfortunately. So I think I'm almost out of time, but maybe I should say that actually this piece that floats around at the end, of course, because this guy is a total conjugacy invariant, and what you do is you build the conjugacy invariant for G and you build the conjugacy invariant for F. This means that actually, if you're trying to do sort of lots of these conjugacy tests, you can start making big savings, because if you have a big collection of them, you don't have to do the total. You don't have to do each of the comparisons. You don't have to do the comparison for each pair. You just build the conjugacy invariant for each one individually. So in particular, if you've tested, like if F is conjugate to G, And this did take exponentially long for you to do. And you've tested if f is conjugate to h, and again, this took you exponentially long to do. Well, this voucher, this coupon that the certificate lets you get a discount on the computation for means that actually, if you want to do G conjugate, decide if G is conjugate to H, well, what you can do is you can take your coupon for F and G and cut it in half and take the G side, and you can take your coupon for F and H and cut it in half and take the H side, and plug each of those two pieces into Flipper along with G and H, and do this one in polynomial time for free. Okay. But I think I'll stop there. Thank you.
Are there questions for Mark? So this is what happens in the pseudo and author case.
Yeah.
In the general cases, is this certificate essentially the same, or
right.
is it more?
So let me say that you have to do the pseudo and author case, and then you have to do the periodic case. And then for the reducible case, what you need to do is you need to break it down into little subsurfaces and deal with each subsurface in turn. There's some nice result which is like when you have, I have to draw something sort of reasonably high genus. So maybe our surface, sorry, there should be genus in here. So maybe we have H and it reduces along these two curves, for example. Well, if you can build a total conjugacy invariant for this piece and a total conjugacy invariant for the map induced on this piece and for the map induced on this piece, then there's sort of a nice way of writing it down using some kind of graph, something like this. This corresponds to this surface, this to this surface, and this to this surface. And so you have these invariants that you drop onto each of these vertices, and then you get that well, crudely speaking, you get that that G and H are conjugate if and only if there's a graph isomorphism which sends conjugate vertices to vertices with conjugate mapping classes on them to vertices with conjugate mapping classes on them. So you have to preserve conjugacy on each of these things. There's also some extra stuff you have to write on the edges as well, and there's a little extra sort of twist where you have to be careful exactly how what the derivative on the derivative of this map between these two vertices does on the vertices as well. So it's a little, there's some subtleties in there, but primarily it's you have an invariant for each of these pieces, and two guys are conjugate if and only if there's a map which takes there's a map between these two graphs which works in exactly the way you would expect it to work.
Can you do the same thing with markings, replacing the splittings with elements removed and sort of getting sight of the...
Not that I can prove. So one of the great things about Flipper, of course, is that it's sort of very, very easy to go in and swap a few of the parameters in the code that's being run and try out other things. And so what you can do is you can plug in, oh, well, what happens if I do this elementary move instead? And for other things that we've tried, you still get cycles out at the end, but there are some peculiarities. So in particular, maybe the cycles that you get are of the wrong length. You see things like so maybe this sort of nice pattern here where I have a cycle of length 5 at the end. Well, when you do this with a different type of combinatorial move, all of a sudden you now have a cycle of length 15 at the end, and it's you're on some kind of like threefold cover or something. It's there's some peculiarities in there that I don't understand, but there seems to be sort of experimental evidence for. So maybe there are other generalizations that you could approach using this.
So at the beginning you said, well, if they are conjugate, we could give the conjugating element.
Yeah.
But this basically says that it's not necessary.
It's not necessary, no.
Okay. Can you construct the conjugating element?
Right.
Line over time?
So
Or
if we,
line over?
yeah. So
Okay.
if you build this guy here, and you also, so this is for H, and you build 1, 2, 3, and you build this guy here for G,
Yeah.
and you have some kind of, and you have some map which takes this cycle to this cycle, then the conjugating element is, well, you go down this bit, you get mapped to here, and you go back up this bit here, and that's the conjugating element that takes 1 to 0.
Well, let's save other questions for privately afterwards. Let's thank Mark again.
There will be a dinner on Wednesday, not today, at Radio